Binary star systems. A binary star system consists of two stars revolving about their common center of mass. It is estimated that about 85% of stars in our universe exist in binary systems. So our sun is comparatively rare in that regard, since it does not have a binary partner. Assuming big M is greater than little m in the picture here, depict and label the first sentence of part A, that is, where the center of mass is. Show the orbital path, assumed circular, for each star, and label the radii of the orbits as r little m and r big M. The center of mass, then, is going to lie closer to big M. Perhaps it's going to be right about there. Big M will be going in a circular path around that center of mass, kind of like that. Little m will also be going in a circular path, so the radius of that one is going to be about there, which means it's going to end up right about there. These are supposed to be circles, sorry about that, like that. And so here we have r big M, and then right there is r little m. Let's answer these questions. Which star has the larger period of motion? And the answer is it's a tie. These two take the same amount of time to go around. They always stay opposite each other. The center of mass is always between them. It's always a straight line between the M's, with the center of mass lying along that line. So the period of the motion, it's a tie. Who's got the larger tangential velocity? That's going to be little m, because it goes a much larger distance around in the same time. Which one has the larger force of gravity on it? Ooh, if you get this wrong in my class, you are in big trouble. It is a tie. The gravitational force is an interaction between two masses, and that force is equal. Now, it has a greater effect, doesn't it, on little m. So little m is going to have a greater acceleration, but the force of gravity is the same. Demonstrate mathematically for this figure that both stars have the same orbital period. We first need to locate where the center of mass is. The general equation for any center of mass is 1 over the total mass, and then we want the mass of one thing times its x-coordinate plus the mass of the other thing times its x-coordinate. And just for convenience, I'm going to say that right here is where x equals 0. So right now, the 3m star is at an x value of 5r. So if we do this, the x center of mass is going to be 1 over the total mass. So that's going to be 1 over 5m. And then we're going to go the first mass, which is 2m. What's its x-coordinate? 0. Plus the other mass, which is 3m, times what's its x-coordinate? 5r. The m's all cancel. I'm seeing 15 divided by 5, which is 3. 3r. That's where the center of mass of this system would be. 2.5 would be about right there, so 3 is going to be right about there. There's our center of mass, and the orbital radius of each of these, that's going to be a total of 2r, and then that's going to be a total of 3r. Now, we're asked to show that these have the same orbital period. So let's do that if we can. Got that picture there? Let's deal with 2m first. What's the force on 2m? The force on 2m is the force of gravity between these. So I'm going to cut a few corners here, so I hope you can hang with me. The net force on 2m is the force of gravity on 2m, which is big G times 2m times 3m divided by the distance between them squared. The distance between them is 5r. So 5r squared would be 25r squared. That is the net force on 2m. And according to Newton's second law, that net force should equal the mass, 2m, times the acceleration, which is v squared over r. What is r for 2m? It's the radius of its circular path, which is, in our case, 3r. So this is Newton's second law that I'm showing right here. F net, gravity, there's the mass, there's the acceleration. If we simplify this, the two m's will cancel. That r cancels one of those, and we end up with the velocity of 2m. I'll label it. The velocity of 2m is going to be, we got to bring this 3 up here, and so that's going to be 9/25, but then we're going to end up taking the square root, which is 3/5. So I'm seeing 3/5 square root of gm over r. All right, you check and make sure that we're okay with that. The square root goes all the way down like that. That's the tangential speed of the 2m star. Well, if that's this tangential speed, isn't it also true that velocity is distance over time? And what's the distance that 2m will go in one time around? It's equal to 2 pi times, what's its radius of motion? 3r. And that's the period of the motion. So that velocity and that velocity should be equal to each other. Now we got a few things that can cancel here. That 3 cancels there. We can put that 5 up there. And your math teacher probably wouldn't be too happy with me on this, but I'm just going to do a little bit of non-standard math here. Instead of dealing with simplifying the r's, I'm just going to leave it like that. You check it out. That time is going to go in the numerator. The 5 times the 2 gives us 10 pi multiplied by r, and then divide by this square rooted thing. That is the time that it takes 2m to go around once. Now we're going to do the same thing for the 3m mass. So here we go. On 3m, the net force is the same. Big G times each of the masses divided by the distance between them squared, which is 25r squared if we simplify that out. And that should be the mass, which is, this time it's the 3m mass, multiplied by the 3m's centripetal acceleration, which is the velocity of 3m squared divided by its radius. Well, the radius of its motion, you can see on the right side there, is 2r. Again, we can cancel a few things here. When we solve this, we get the velocity of 2m, sorry, the velocity of 3m, excuse me. That turns out to be 2/5 square root of gm over r. That velocity of 3m is equal to what? Well, it's equal to the distance that 3m travels once around, which is, you ready for this? 2 pi times its r, which the r of its motion we've said is 2r, divided by its time. What does that give us? I don't know. What can we do here? I'm seeing the 2's canceling. There, 2 cancels that one. This 5 comes in the numerator, giving us, oh, there's a 2 right there. So that's 10 pi r in the numerator. Uh-oh, look at that. I know I'm going a little quickly here, but you can always stop the video and check we're okay here. But look at that. See that? That time right there, that's the time for 2m to go around. And this down here, that's the time for 3m to go around. They are the same. So that's pretty neat.